Okay. Hello, everyone. Today is the last lecture, and I only have one announcement, which is about the quiz. The official deadline of the quiz is today at 11:30, but as I mentioned in my email, we'll accept late submissions until Friday. Yeah, so that's pretty much it. Let's jump into the course, into the lectures. So the plan for today is to finish file systems, and then as much as I can, I will cover reliable storage. I doubt that I can finish all the slides, so I might jump to cover all the basics, but won't go to the details of some of the concepts. I would trust you that you can, look into the book or the slides for more details. Okay, so with that, let's jump into the lecture. Okay, so before I continue, I want to make a few clarifications about previous lecture. So with FAT, one thing that I sort of forgot to mention is that I guess let me go back. So I actually added this slide, which tells us the roadmap that we're going to have from. We're going to get a file name. We're going to look into the directory data structure to get a file number. And then given a file number, we're going to look into the index structure to get storage blocks. So this is basically the roadmap. So we talked about this the directory. We talked about having a linked list implementation of it, or implementing it with B+3 data structure. And for this index structure, in the last lecture, I talked about FAT, FFS, and NTFS. So this is basically where we are. Now, one thing to clarify with FAT, the file number that we're going to give every file is basically the index of the first entry in FAT that corresponds to the first block of this file. So let's say so because this entry in FAT entry is the first entry of this file, this whatever file it is, the number we're going to give it is the index of this entry, the first entry. Let's say the index of the first entry is 31, then the file number for this file becomes 31. And let's say we want to, allocate a new file. Let's say we pick one entry to start to create that file. Let's say that entry is entry 63, then the file number becomes 63. Okay, so that's one clarification. The second clarification I wanted to make was about NTFS. So here, I guess two clarifications. I don't want the graph here to confuse you, especially the way I talked about it. When I talked about it, I started saying that, oh, let's say, I guess I'll talk about that one in the second slide, but let me do the first clarification about this STD info. I sort of alluded that this is like a metadata. It is used for some metadata, but as we will see in today's lecture, the way that NTFS stores metadata is a little bit more involved. than just using this field for it. But we definitely keep pointers to metadata here. And we keep some metadata here. But then we have another way of a more comprehensive way of keeping metadata, which I will talk about today. But anyways, so this std info is basically just a limited amount of information. We can include pointers in it to some more comprehensive metadata for our file. And last clarification is in this figure. When I was talking about it, I said when your file goes through stages, you start like this, and then you go through this, and then here is where things get really fragmented. One thing to note is it's not like we'll have all of them, right, for the same file, because as you can see, this one has its own MTF entry. This one has its own MTF entry. So I did not mean that at the same time we'll have multiple of these entries for the same file, like this. You might have this case, or you might have this case where you have multiple MTF entries for the same file, but you can't have a case where you have, a resident data and a non-resident data at the same time for the same file. So basically what I mean here is ignore. It's kind of like just an illustration to think about. I mean, the best way to describe it is if you think about all four cases as 4 different files, that would make it easier to understand. So this would be one file that is a small. This is another file that could be big or small. And then this is a fragmented file, and this is a super fragmented file. So if that makes it easier to understand. Okay, so with those clarifications, let's now jump into the new stuff. Okay, so okay. Keeping here. Great. Okay, so now, very related to one of the clarifications that I did, we're going to talk about metadata in NTFS. So the design actually puts almost all of the metadata in files, in well-known file numbers. So examples, for instance, file number 5 is used for the root directory. This is not much metadata, but then, for instance, the free space bitmap is stored in file number 6. Now, for access control, there is a file named secure, and the file number is 9. So the way it works is in this file, you have all different types of access control. So let's say if in your system all files have the same access control, then you would have one entry here that would correspond to that particular access control that all files have. But if you have like different access controls, like for instance, you have files that have read-only access, and then you have files that are read and write, they have read and write permission, then you would have 2, for instance. So basically a list of all possible access controls that you could have in your system, you store them here, you give them a unique key, and then in your MFT record, you just hold that unique key. So what is the access control of this file? It would be just a number that would correspond to one of the entries in this file. The MFT, the master file table itself, is stored in a file with a well-known number 0. So that's that. The allocation policy is best fit. Yeah, this is a feature that NTFS has and not many file systems have. NTFS allows users to specify at creation time what they expect their file size to be. And that's sort of important when you're dealing with extents. You sort of want to allocate, maybe pre-allocate an area for this file. If you know that this file is going to be a certain size, you might want to keep those contiguous regions for this file. If you don't know and you get if you don't allow users to give you this information, alternatively, you could just either be pessimistic, give the file the smallest extent, which would going forward mean that you might end up fragmenting the file, or be optimistic, give the file define optimistic and pessimistic the way you want, but the alternative is to give the file a big space to avoid fragmenting it in the future, but then that's also wasteful. So NTFS allows users to specify how big their file will be eventually at the beginning, which is kind of something very that would come handy in some workloads. Like the other ones, like FFS, NTFS also reserves a fraction of the volume for itself, more specifically for MFT, because it doesn't want MFT to be fragmented. So you want to have enough area to store MFT. Yeah, and then I think I mentioned this. It's possible to defragment NTFS the same way that we defragmented FAT. You could do this as well, given the history. So they're just from the same family. So they preserve this feature. And here is basically a summary of almost everything we saw. So we have FAT, FFS, and NTFS. The index instruction in FAT is linked list. In FFS is a tree. It's fixed size and asymmetric. NTFS is a tree, but it's dynamic. The size could change as you go. Granularity in FAT is blocks, in FFS is blocks, in NTFS is extents. So the unit is extent that the file system works with, or not works with, stores files with. Free space tracking and management with FAT, we saw you have to always just scan your entire FAT array. With FFS, you store bitmap for each group in a fixed location cell. And then with NTFS, as we saw, you still have a bitmap, but this one is in a file. With locality, FAT is very defragmented. It could become really fragmented. So to provide locality, you should periodically run defragmentation. With FFS, we saw that they basically divide your storage into groups and try to fit each file close to its inode structure and free space bitmap structure to create some some notion of locality. And with NTFS, locality is in upfront, so you actually have the notion of extents, which is based on allocating contiguous region to files. The way that you allocate is basically best fit, whereas in FFS, you were doing first fit. And then you still could get defragmented, where you can run defragmentation. You could still get fragmented, so you can run defragmentation. The last topic I want to talk about with file systems is, again, caching. So if you look at what kernel does when it comes to files, when you read files from the storage device, usually you call a system call, and that traps to the kernel. Kernel wakes up the driver, or tasks the driver with the data it wants, and then the driver tasks the controller, and then the controller activates the device, and with whatever method of data transfer, let's say DMA, you copy the data to kernel buffers, and then you raise an interrupt. Then again, interrupt handler wakes up, realizes that the data is ready. It copies it now to the application's buffers or memory, and we're done. I mean, we can make the application ready to use those files or the data that it wants. Now, in this process, the operating system is to find which blocks of the file, to know which blocks correspond to a file, and where each block of the file is stored. The operating system has to consult the file system data structures, the directory tree, and the index structure. So, and where are they? Those are also in the disk. Now, you could potentially see here a possibility to speed up everything by caching the translations here, from file names to file numbers, and from file numbers to blocks. And that is basically called buffer cache. So you could also possibly use it to cache blocks of files. If there is a file that is constantly being accessed, you could cache the content of that file as well. But more generally, you can cache your directory structure. You can cache your inode data structure. You can cache anything that is related to the file system. And then you can actually modify it, right? If you are creating a file, you're basically modifying your inode. If you're writing to a file, you're modifying your data blocks, and so on and so forth. So everything we talked about, caching translations and caching data, all are relevant here as well. So we can use memory, DRAM, as a cache for storage now when it comes to file system. And that is called buffer cache, which allows us to exploit the locality that may exist in the storage data. So many operating systems actually have this. And it actually helps speeding up the performance of your operating system and kernel. One thing to note is that unlike TLBs and your, L1, L2, L3 caches, this is entirely implemented in software. So the hardware doesn't know about it, right? Now that it's caching, then our usual questions come in again. The most important one would be, what is the replacement policy? If you have a limited cache and you keep working with your storage, I mean, we saw that storage could be terabytes, and we have actually limited DRAM space. So at some point we have to evict data and bring new data. Here you can use LRU, and because everything is in software, we can actually afford doing actual LRU instead of what we did with paging, which was approximating LRU with clock algorithm or second chance algorithm or nth chance algorithm, which were just, approximations for LRU. Here, because everything is in hardware, is in software, we can afford adding a bunch of bits and tracking which data structures have been used the least. So here we can actually have LRU. It works well. I mean, we saw that it's one of but LRU by itself is an approximation of mean. So it's something that we can use. The problem with it is that it may not be the perfect policy when it comes to file system for some workloads. In one of the quiz questions we had, we asked you about, a program that goes through an array, entries of an array that, is bigger than your cache size. If you have that scenario, then LRU is nothing better than first come, first serve. So LRU becomes first come, first serve. And that scenario could actually happen in some workloads when it comes to file system. Here is an example where you're, going through all the files in a directory, searching for searching for a name, for instance. So basically, by doing this, you're basically going through the inodes of all the files in your directory. And if it is a big directory with a lot of files, then caching inodes would just not be efficient, because you're not going to reuse them. You're reading them and you're just interested in knowing if a certain word exists in the file name, and that's it. You don't have locality. So yeah, keep that in mind. So LRU in those cases becomes like just FIFO. You could implement other policies if you want. One policy would be like something like use once. So basically not caching at all. If you have something like this, then essentially no caching is actually helpful. So you can just ignore caching it altogether. Now the other question that you have to answer is how much memory you should dedicate to your buffer cache. So if you dedicate too much memory, then you're basically cutting off from processes memory allocation. So you might end up having the situation where processes start thrashing each other or themselves. So too much memory for cache buffer means less memory for processes, which is not good. If you have too little memory, then your cache becomes really not effective. It becomes just a burden. And so one thing that you can do is to just dynamically adjust how much memory you give to the buffer cache. So if you constantly check the paging rate, so see how often you're evicting pages from processes, and that tells you if you're not evicting at all, it means that processes are happy. They have they have enough memory to run all of them. But if you have a lot of paging, meaning that you're evicting pages and bringing pages back from disk, this means that you don't have enough in memory for your processes. So by just looking at your paging rate, you could decide how much memory to allocate to the buffer cache. The other thing that you have to pay attention to is prefetching. It actually makes a lot of sense with files, prefetching. Usually, as we saw with access patterns, file access patterns, when you're reading a file, you usually read sequential blocks. So prefetching makes a lot of sense. But again, you have to be careful how much to prefetch. If you prefetch a lot, you might be wasting your buffer cache with data that is not being used. And if you prefetch too little, then you're not taking you're not utilizing the opportunity to your advantage. The other important aspect of buffer caches is delayed writes. Like any cache, any other cache, you have to resolve what you're going to do with writes and dirty entries, dirty blocks. Here, if you let's say you have cached an inode, and then you have added some data to that file. So you expanded the size of the file. So inode has changed. So first you cached it, then you read it, and then you made some changes. Maybe you wrote to that file, and now the inode has changed in your cache. Where is the cache's memory? Now what are you gonna do? So the writes have been gone through the memory. Now you want to permanently also write them to your disk. Usually buffer caches are write back, meaning that we don't go and write it to the disk until we want to evict that entry. But this is potentially risky, because what if there's a crash? So what if your DRAM is volatile memory? So if you lose power or your system crashes, then all the changes that you made are gone. To deal with that, usually Linux systems have a kind of like a periodic write back process where you just look at all the dirty blocks and you write them to the disk, and it works roughly every 30 seconds. So every 30 seconds you write your data back to disk. So this is also a trade-off, right? If 30 seconds is a lot of time, and if a failure happens, you could lose 30 seconds worth of data. So it's risky. One solution is to just not have buffer caches, as we'll see going forward with reliability. Yeah, so another thing here is that you might not want this 30 seconds to go down either, because you might actually have really short-lived files, like temp files that you create, or you create temporarily a file and then you delete it. So in this scenario, using cache makes a lot of sense because that cache buffers the writes to filters. Sorry, the cache filters the writes to the disk, and we saw that writes are very expensive in both disks and flashes. So filtering them is something that we would want to have. So if you decrease this 30-second, let's say to every microsecond, then you would end up writing these temporary files where you don't really need to. So there's a trade-off here as well. Like always, we always have trade-offs. Okay. Yeah, and I basically talked about the crash that could happen, which actually sets the stage very well for the next lecture on reliable file systems, which we'll talk shortly about. So to conclude this lecture, I guess I'm going to have this slide in the next lecture, so we'll see it in the next lecture. Okay, so yeah, so let's jump into the final lecture on reliable storage. I will try to cover all of these as much as I could. I may have to jump, obviously. There are many slides, and I don't have enough time. But hopefully, slides are self-explanatory, and if you have questions, definitely do not hesitate. Either use the Piazza or email me if there are any questions. And there are great. So the book is very comprehensive on this. I would strongly suggest reading this last chapter from the book, given that I'm not going to have enough time to go through all the topics. So what we're going to see is the problem that we might have with failures. We've already set the stage, so I'll just talk a little bit more about what could. I give you examples of what could go wrong. We'll talk about transactions and the ASID properties of transactions. I'll briefly talk about, hopefully, transactional file systems and copy on write file systems. And eventually, if I have time, I'll talk about RAID. Now, there are three abilities that are very important: reliability, availability, and durability. These are actually quite different. I'm not going to spend time in describing each one of them, but you could potentially have a system that is highly reliable, but absolutely not available, or highly durable, but not reliable. Sorry, that one actually, never mind. So durability is part of reliability in some sense. Anyways, so let's see what happens with system failures and file systems. So let's say you want to create a file. This single act of creating a file is translated into a bunch of operations, right? You have to allocate disk space. You have to modify your free bitmap. You've got to set some pointers, like let's say if you have FFS, you have to set a bunch of double indirect or triple indirect pointers. So that's that. So the single file creation has bunch of stuff, bunch of operations, bunch of updates to the file system. Now, what happens if in the middle of creating a file, you have changed your, let's say you have changed your directory structure, but you haven't changed your bitmap, let's say, and then your system crashes. So in the middle of creating a file, your system crashes. Now, if you come back from that crash, you have inconsistency in your system. Your file system says something, your bitmap says something else. And this actually was very commonplace back then. I would say a decade ago, decades ago, not 2 decades ago, a decade ago. If you would have a flash disk and you were in the middle of transferring files to your flash disk, and then you would immediately plug it out, or if your system would for whatever reason die on you, then you wouldn't be able to use your flash disk anymore because your system was not reliable enough. So there would be, when you would connect the flash to your system, there would be some inconsistency within the file system. So let's say the directory structure would say something that was in contrast with your index structure, for example. So in this lecture, we're going to talk about ways to deal with those situations. The first thing you could potentially do, it's ad hoc, and it actually was used in the past, is to sequence the operations that you have in a specific order, so that if you experience a failure or a crash, you could run a recovery routine that, given that sequence of well-crafted sequence of operations, would infer what has gone wrong, if anything, and then would try to recover from the failure, make the file system state consistent. So here is an example. Let's say you want to append data to a file in FAT. So this is a sequence of operations that have been put together in a specific order that would make it easy to recover from. So you could, I guess I'm gonna jump. So let's look at one that is interesting with FFS. Let's say you want to create a new file in FFS. So these are the things that you would do in sequence. You would allocate first your data block. You would write to that data block. Then you would allocate an inode. So after you write, you allocate inode. And after you allocate inode, you would write your inode block. And once you write your inode block, you would change the bitmap for inodes. And once you're done with that, then you would add that file to your directory. And once that is done, you take a snapshot of time when everything was done, and you save that as the latest time that this file was modified or was created. Now, if you experience a failure anywhere here, you could see that you could detect where exactly you failed. You can scan your inode table. If you have any unlinked files there, what that means is that if you have a file in your inode but nothing in your directory, you can safely delete the file. You can detect it, right? Because adding it to directory happened after creating the inode. So if you have now an inode that doesn't show up in the directory, you can just delete the inode. You still lose data, but at least you keep your system, your file system state consistent. You could then compare your. So we're done with this part. So let's say this is okay. Now, if you have, if you compare your free block bitmap against your inode tree, then you can actually see, because it happened afterwards, so you updated the bitmap after this. So let's say if you have a bitmap that doesn't show this, you can detect it, right? You can detect that you failed here. You have created the file, but you haven't started the bitmap. So either you can reverse this or just go all the way through. Now, the problem with this method is the recovery time is very proportional to your storage size. You have to go through all your inodes. You have to go through the inode table. You have to go through all your bitmaps. And this is basically a time-consuming process that could take hours and hours and hours and hours. And that's basically the main reason that this method is no longer used, because people don't want to wait that long for their system to recover from a crash. This method, though, is still used to some extent with applications. So let's say if you're working on a Microsoft Word document and your system crashes, usually the application does some notion of recovery. Most of you have probably experienced this, where after a crash, your application asks you, do you want to recover the file that you were working on, or it does it automatically. So it still could be used. So it's nice to have some general rules of what we should do if we want to have our own application with a recovery procedure, and we don't want to use more fancy methods that will come later. Then here are some general rules to follow, which I will leave to you to study. There are more, so these are some rules to get to know. What is good about careful ordering? It doesn't require any support from the storage drive. You can basically do everything in software, and it works fine for most of multi-step operations, especially if you don't have a big storage. So it shouldn't give you a headache. But as we saw and discussed, it's really time consuming. It could potentially make your updates to your file system time consuming, because you have to make sure that one operation has been permanently saved before the next operation. So especially if you're working with the storage system, you usually have write buffers where your writes are buffered in either in your memory. We talked about cache buffers, or inside the device in the buffers before it's permanently written into the sectors. So you want to, usually if you want these methods, you have to use, you have to enforce the device to write your updates before you start writing other stuff, and that is that could lead to inefficiencies and could slow down your updates. The other problem with this is that it might be hard for some operations to come up with this, handcrafted sequence of operations that is safely interruptible. So that's another thing. And lastly, whenever you turn one operation into a bunch of updates and operations, you basically increase the possibility of interference between multiple concurrently running operations. So let's say you are creating a file or updating a file in one process, and in the other process you're reading from it or you're moving it somewhere else, and these could interleave. The same problem we had with critical section. So now your inode structure becomes the critical section, and it's just hard to achieve some sort of consistency model on this with just going with ordering the operations. Basically, in some cases, it's impossible to have some notion of mutual exclusion. And lack of mutual exclusion when you have shared data causes all sorts of problems. Okay, let's actually take a break. See what time it is. Yeah, let's take 2-3 minutes of break and then we'll continue. Okay. So let's continue. So an alternative way to have to implement reliability or to have a reliable system is to use transactions. Now, what are transactions? So a transaction is a group of operations that provides ASID properties. That's in one sentence. So now, what is ASID property or properties? Sorry. The first one is atomicity. Sorry for that. So what you want is for your operations to be atomic. Yeah, so, and by that we mean logically atomic. So basically you want it to logically either all of the operations happen or none of them happens. You don't want a bunch of them to happen and then a bunch of them not happen. So you have to keep in mind that each operation that you might have in physical level by itself is atomic, could be atomic, but to get a group of operations appear atomic, we need to do some tricks, right? So we want to have a logical notion of atomic operations. We'll see more on that. You want also consistency, meaning that if you have a system, if your data is if your system is in a legal state, whatever legal means in your application, you want your transactions to move your system from a legal state to another legal state. You don't want to have a legal state and run your transaction, and then as a result of your transaction, your system becomes goes to an illegal state in a way that your data is like not consistent with what you want. For instance, you can't get if a transaction is like a bank transaction, you don't want to have negative balance on a debit card, for instance. Or you don't want to schedule a meeting on February 30th. Okay. The other one is isolation. Isolation means that you want your transactions to have no side effects on each other. And that basically means that if you have two transactions that are executing concurrently at the same time, you want them to appear as if one of them ran before the other one. That way, you know, the one that ran first commits its updates, and then the one that ran second commits its updates. Again, logically, they could be doing it concurrently. But as long as logically it appears that they ran sequentially, you have that notion of isolation. This is a sequential execution, or logically executing a transaction in a sequential manner is a very restrictive notion of isolation. There are other notions with more relaxed definitions, as we saw with memory consistency. Here also the same notions apply. And finally, durability. Once a transaction commits its updates, you want those updates to be permanently saved. So that's where you get the ASID properties. So a typical structure for transactions is you begin your transactions, you do bunch of updates. If something fails, you roll back, or if there is any conflict with other transactions, you roll back. If none of that happens, then you can commit your transaction. So here is a very classic example where you want to transfer X amount of dollars from someone's account to someone else's account, and you want this to appear as a transaction. So either both of these happen or none of them happens. You don't want to have a situations when just one of these two happens. So you want either all of them to happen or none of them to happen. One of the ways to achieve atomicity and durability is by redo logging. This is one of the most common ways to achieve these two. And what it is that it actually has 4 parts plus recovery. So what are those 4 parts? The first one is prepare. Basically, you have a log file where you log everything that you do. The reason it's called redo logging is that we're going to do updates at least twice, in some cases more than twice. But how it works is that instead of actually applying your updates to the actual data, you just log the changes that you have made in a log file. And then once all your operations are done, are logged, then you append a commit record to your log. So with the assumption that you can actually write this commit to your log file in an atomic way, this would be a single disk write, for instance. What happens is after this commit is written in your log file, you want all the operations to actually now be permanently executed on your data. So this is where you do the redo. Why is it redo? Because you've already wrote your changes in a log. Now you take them from the log and you permanently write them to your actual disk and data. And then you garbage collect your log file. You remove all the logs that you have. Now these are the 4 steps for redo logging. Now if you fail somewhere before you write the commit record, or after that, you could fail here while you're appending updates. You could fail once you're done with all of them, but before you commit, you could fail here. You could fail after commit and before redo. And you could also fail after redo before garbage collection. And if you fail after garbage collection, that's easy. You're done, right? So depending on where you fail, immediately after you bring your system up, you start the recovery routine. And what it does is that it goes through your log. So this log has to be in permanent storage. So that's why it would be available after recovery, because it's permanently written. Now you go through all the records in your log file, and you do the following based on the type of that record. So if that record is just an update, so if it's one of these, then you add it to the list of updates that you're planning to do. If the record that you read from your log is a commit record, so that means that you failed here after a commit, then at this point, you can, in your recovery, you can actually go ahead and redo all of these. So you can now permanently write them to your storage. And if you see a rollback record, that could happen, like let's say it could happen here, where your system detected an interference between two transactions and then wrote a rollback for one of them, but then before the rollback happens, or the request or the record is processed, you've crashed. So if you get a rollback record, then you just discard all the updates you've seen so far in your recovery routine. You were creating a list of all the updates that you've seen for this transaction. Now that you see a rollback, you just discard it. If you see a commit, you can go ahead and commit the transactions. Now, if you go through all your logs, and for some of the transactions you don't see the commit at all, that means that the system failed here before the commit was recorded, so you can just again discard. So even though you didn't see any rollback on that transaction, but because there was no commit for it, you can basically discard all the changes. And once you're done, you can garbage collect. So one thing here is that the way that you're implementing logging, the redo logging, it should be the case that writing the same update multiple times shouldn't, change the state. So one example is, with the transaction that we saw, that you get $100 off of someone's account and then you add $100 to someone else's, your record should be something like Mike's account should be 200 or 100. It shouldn't be, your record shouldn't be Mike's account is Mike's account plus 10 or plus 100. Because if you then run this record multiple times, you could just keep adding $100 every time you run it. Whereas if it is just, oh, Mike's account should be $200, then no matter how many times you execute this update, you're not going to add to Mike's account more than whatever you're supposed to, or subtract from Mike's account more than whatever you're supposed to. Here is an example. Let's see how much time I've got left. Okay. Yeah, I guess this example would make things easy to understand, so I'm going to go through it. Let's say Tom's account is 200, Mike's account is 100, and this is what you have in your memory as a cache of your non-volatile storage. As I said, the log file resides in your non-volatile storage. It has to be permanently saved. Now, let's assume that you have, you're done with your prepare stage, where you have written all the updates that you need to do. So you want now you want Tom's account to be 100, Mike's account to be 200, basically transferring $100 from Tom's account to Mike's account. But still, you haven't logged commit at this point. So you have this stage. Next, you log commit. So you write commit at the end of this log file. What happens next is now it's safe. So if you look at the state, your cache already has the changes that you've made. Your storage, in your log file, you have the changes, but still not completely executed into your actual data. So after this commit, now it's safe to write your logs to your data, where you can do that. And once this is done, you can garbage collect. You can just remove them all from your log file. So here is a slide on details of how you can implement this. I'm going to move on. Next topic is, okay, we kind of saw how you can get atomic and durable transactions. How can you guarantee isolation? So I'm not going to talk about consistency because consistency sort of is application dependent. So whatever consistency is makes sense in your application, you have to make sure that at the end of your transactions, you make sure that you're transferring your system from one legal state to another legal state. So that would be sort of with the programmer. Now, the other thing that the system has to provide is isolation to have transactions. You still want to make sure that, you know, if you have concurrent transactions running at the same time, you don't want them to have interference with each other. To have isolation means that if you have two transactions that are working on the same data, you want to implement mutual exclusion. So with mutual exclusion, you basically make sure that one of them gets to do it first, and then the other one gets to do it second. Now, this is a little bit more restrictive than just mutual exclusion because you might be working with multiple objects, not just one object. Like if you have a bank account, each account value is an object, and you might have transactions that involve so many accounts. Let's say the university is paying TAs or paying, you know, students for research, undergrad research, whatever that is. So in one transaction, university wants to the bank wants to get money out of university's account and put it in students' accounts. So there are a lot of objects. So we want kind of like a mutual exclusion on all of them. One way to achieve that is two-phase locking. Again, I'm not going to go into details of this, but it's kind of like the way it works is you divide your operation into two phases with a well recognizable boundary. So up to some point in your operation, you only allow each process to acquire locks or mutexes. So at this point, if you have acquired some lock and you need some other locks, let's say you have acquired lock on Mike's account and now you want a lock on Tim's account, so you cannot release any lock. You have to just keep on, even if you're done with whatever you wanted to do with Mike. Let's say you have updated, I mean, you have executed the update on Tim's Mike's account, but you haven't yet done it on Tim's. You cannot release the lock that you have on Mike. You keep that, you acquire all the locks that you need, and once that is done, you do your updates, and then you start releasing your locks. So the first phase is called expanding phase, and then the second one is contracting phase. So during expanding phase, you only acquire locks, you cannot release any lock. And during the contracting phase, you only can release locks. You cannot acquire any more locks. And you can easily see, if you analyze this, that this would indeed provide isolation as we want. So if we make all our transactions implement two-phase locking with the constraint that they cannot release their locks until after the entire transaction is committed, you will definitely get a two-phase locking. So all the way to the end of the transaction, your transaction can only acquire locks. And once the commit is written, your transaction could release all the locks. So in such system, you can definitely see that it prevents any other transaction to see the results of one transaction before it commits, because in order for them to see the result, they have to acquire the locks that transaction has, and they cannot acquire the locks until the transaction releases those locks. But this could easily lead to deadlock, as you saw in ECE 252. Fortunately, it's easy here for us to deal with deadlocks. We can just detect them. You probably remember deadlock detection mechanisms. So once you detect, because you have transactions, you can roll back your transactions easily because of them being atomic. So if you have a deadlock, it means that your transactions cannot commit. So anytime until your commit, you can roll back easily. And good thing is, given two-phase locking and redo logging, you can implement transactions and get ACID property, again, with the C part of it being the job of the programmer to make the transactions consistent. Now, we talked about all of this, but if you remember, we started with file systems as our use case for transactions. So now transactions could be used in file systems. How many? Okay, I have 5 more minutes. So there are two major ways to use transactions for file systems. There is one category of file systems that are called journaling file systems. So they use transactions for metadata. So every time metadata is being changed, let's say by metadata, I mean here anything other than the actual user files, data blocks. So file directory, all the indirect, everything about inodes, everything about access control, everything other than actual users file data blocks. You use transactions on them, and that gives you journaling. Examples are NTFS, Apple HFS Plus, Linux's XFS, and JFS. Also, ext3 and ext4 have journaling as default method for transactional file systems. Now, the other category is logging or full logging. In this one, you just use transactions for both metadata and data. And one example is, like, two examples are ext3 and ext4. You can actually configure them to, instead of being journaling, be full logging. Here I have another example where I use transactions to show how you can create a file, for example. I'm not going to go through it. You can definitely look at the slides. They should be self-explanatory. Okay, now another example of reliable file systems, or another implementation of reliable file systems, is the concept of copy on. Typo here. So the concept of copy on write file systems. So these are file systems that are written from scratch with transactions in mind. And the way they work, I'm going to just give you the gist of it. I can only scratch the surface. Every time you make an update, you you don't do it in place. You create a new copy, a new version of your file system in parallel with the old version. And once the entire transaction, the entire update is done, or set of updates are done, then you sort of commit and then garbage collect the old versions, and you are left with the new version. So I'm going to just show you an example. So this is what we saw previously with FFS sort of file system, where you have your inode array, and then you have direct and indirect blocks, and then you have your data blocks. Now, with your traditional file system FFS, for instance, as we saw, inodes are located in a well-defined location on your disk in each group, right? Now, if you want to do what I just said, creating a different copy of your file system every time you make an update, so you're going to just make a copy of everything that you're going to change, your inode array included, so you can't really possibly have this in a fixed place. To deal with that, you can have something like this, where only your root inode is in a fixed place, but then you put your inode array in a file. So you basically use indirection to get to this file and read your inode array. Again, I can't go to more details. If you're interested, definitely look at the book. Now, so this is now a new version where you can actually implement copy on write. Now, let's say that you want to write into this data block. What you do, instead of doing it in place, you make a copy of it and you write your update in this copy instead of writing it in your old one. Then you create a copy of all the indirect nodes all the way to your inode file, because this has changed. So this is now not usable anymore. You don't want to change this and make it point to this new one, because you don't want to change anything in place. So you have to create a copy of this as well. Now that you have created a copy of this, you have to also create a copy of this one. And now that you created a copy of this, you want to also create a copy of this one. So you end up creating a copy of all of these, all the way to here. Now, at this point, the last thing you're going to do as your commit is to create a copy of your root inode. Now, this would just be like a commit in transactions, as we saw, kind of like committing all the changes that you've done so far. If this doesn't happen, then you can just ignore all the changes and you still have a valid state. So the difficulty here is that you probably want to have a limited space here for your root inode slots. So usually you keep like some space for these inodes, and then you add checksum and a version number so that you can track which one of these inodes is the most recent one. And potentially when you go down, you can just come back and rewrite on the old ones because they're just not used anymore, right? So if you crash, you can just check the version number and the checksum to find which one of these slots is the current version that you can use. You can do a bunch of optimizations as well. So you can batch a bunch of updates. Let's say if you want to make some updates not only to one data block, you can batch them together, because then you can save here on these blocks, right? You have to change these blocks. So if you don't batch them, you will have to write one version for this file, then another version for this file, and then another version for this file. So you would end up creating 3 copies of these, one after another. Whereas if you batch them all together, you can just amortize that cost and have one copy of these 3 for all of them in one file. And if you have different files that are being changed, you could also save on, let's say if another file here changes, so another inode also changes, then you could also save on everything from here to your root inode. So you could amortize cost on those as well. The other thing about this is that you might think it's the performance is really terrible. In practice, the performance is not that bad. One reason for this is, so here what you have is in a usual traditional FFS FFS-like system. As you remember, you had your bitmap and inode in a particular position in your group. So you would update them, and then you would go update these new data that you have, the new data blocks that you have. So you would update them in place. So this is how it works, and you actually end up seeking, right? Because they're not necessarily sequential writes or sequential reads. Now, with copy on write, the luxury that you have is that everything is mobile, basically. You don't have fixed location. You only have fixed location for your root block. The rest of them can be anywhere on your disk. So what you could do potentially is, once you know the updates that you want to make, you can write them sequentially. If you have, a sequential region of your disk empty, you can just write them all sequentially, and that boosts your performance really greatly. In some cases, it actually gives you better performance than traditional files. There are definitely some, yeah, and then you do garbage collection. So yeah, it's the advantage of this is that it gives you really good reliability, fast recovery. You don't really need to, go through a recovery process, going through, complexity of ordering your operations and reasoning about what could have happened. All you need to do is to check your root nodes, check the checksum and their version, and find the latest stable version of your file system, and you're done. It's very fast recovery, and it gives you a high throughput because of the way you can update. Potential downsides are maybe high latency with your updates. Even small changes require many writes, as you might imagine. And then the garbage collection could become a bottleneck in your system because it's kind of like a extra step that you have to take that was not necessary. It's kind of like very similar to what we had with Flash. Okay, so I'm done. Oh my God, I'm actually too far away from I mean, you guys can leave. I think it's worth talking about RAID as well, so that it's actually on the tape if people want to watch the lectures. I'm gonna go ahead, spend some 3, 4, 5 minutes extra to explain RAID, and then end this lecture. So the idea is that transactions are not gonna bring full durability, because you still could get you could still get your sectors, you could still get bad sectors, for example, right? So you have to have some notion of redundancy in how many copies of your data you save. So the idea is you could use different methods to save copies of your data, so that if one of your data blocks is lost, you don't lose all your information. So that's where the RAID notion comes into picture. So I'm going to talk about 4 RAID methods, starting with RAID 0. RAID 0 provides no durability. So it's just, I'm going to talk about it because it's used in another RAID later on, which provides durability. So RAID 0 basically provides a lot of throughput. So if, let's say you have 2 devices, 2 flash disks or hard disk drives, you could potentially use them in parallel by distributing your data on both of them. This way, you could send reads or writes to 2 devices instead of sending them to one device and making them sequential. You can do them in parallel. Now, the first version of RAID that provides durability is RAID 1, which is basically just a simple mirroring. So for each data block, you keep a copy of it in the other disk. So one of the disks becomes a mirror of the other one. So in this case, if one of the disk drives fail, you still have your data. Now, it's introducing a lot of overhead. You're basically having 100% capacity overhead because of this. And this is not that efficient. So what to do? You could use RAID 5. The idea with RAID 5 is let's minimize or make the redundancy in data more efficient. And the way it works is that let's say you have G or N drives, let's say G drives. You can, on average, use one of the drives. On average, I'm saying it's going to be distributed among all the drives. But average behavior is as if you use one of these drives as the redundant one, and use G-1 for keeping your data. If G equals 2, then RAID 5 is basically RAID 1. But for G more than 2, then RAID 5 is RAID 5 and different from RAID 1. So here is an example. So I use D1, I put D1 here, D2 here, and then I keep a parity, which I'm going to calculate based on D1 and D2 on drive 3. So these are stripes. So that's why it's called striping with parity. Now, in the second stripe, I will have D3, D4, and then parity comes on drive 2. So you don't want to have the parity on one drive because, as we will see, every time you make an update on any of these data, you have to also change the parity. So if you keep one drive for your parity, then you keep writing on that drive on every write. And that could, if that drive is, let's say, a flash drive, that could basically lower the life cycle of that drive. You want to balance your load. That's why you basically in a rotational manner you change which drive keeps the parity for that stripe. How do we calculate this parity? We just XOR the data blocks to get the parity. It's very simple. Now, if you lose D1, you can calculate D1 by XORing P1 and D2. So that gives you leverage, so you can afford losing one drive and still not lose all your data. Then you have RAID 6. What if you, so with RAID 5, the problem is if you have large storages and one of them fails, to recover, it could take a lot of time just to recover the data that you lost. And because it could take long, you could actually introduce an opportunity for another drive to fail. So, and if that happens, then you lose all your data. So you're recovering from one failure and then another failure happens and you're done. So there are cases where you actually want more than one parity. So here is an example with 2 parity. Now, to calculate this second parity, we can't just do what we did with the first parity, because then you would have redundancy in parity, and that's not going to help you. So the way you calculate this second parity, there are algorithms for this. The most commonly used one is a Reed-Solomon system, which actually ends up being a system of equations that you would solve in the case of failure. So you're paying a cost. The cost of reliability and durability is longer recovery time, because when you want to recover your data, now you have to, instead of like a simple XOR, you might end up having to run system of equations. And then finally, I'm going to talk about RAID 10, which is basically a combination of RAID 1 and RAID 0. So here is when RAID 1 is happening. So you mirror your data blocks. And here is where RAID 0 is happening. So now this becomes 1 unit, this becomes 1 unit, and you just distribute your load between the two. Okay, so that's pretty much it. So I'm glad I actually went through all the slides. Now, I want to take a moment and thank everyone for taking the course, and wish all of you all the best with your term, with the exams that are coming, if you have any exams. Yeah, so it was great. It has ups and downs, some hiccups. This was the first time the course was offered. Overall, I would say it was successful. I hope you guys learned something that will be helpful in your careers. Yeah, so next term, we've got a lot of students taking this course. I don't know if it's you guys who, advertise for the course or some other reason that so many students are taking it, but because it's elective, I think, for you guys. But anyways, so hopefully you learned something. Hopefully you had a good experience. With that, this is the last lecture. Thank you, everyone. Take care, be safe, and bye-bye.